section 11.7 strategies for testing. And I hope you can see that screen. Maybe make it a little bit bigger. And this is not being graded, although it still exists. So you want to do practice at it, feel free. It can't affect your grade. I hope it can't affect your grade. I'll make sure it won't. I've made it 0 points. So kind of hard to get a negative out of that. Essentially what you're going to be looking at are questions which are similar to all the sections you've done in chapter 11 to do with series. And the main difference is here that you need to decide what technique you're going to use, what test you're going to use. That's it, right? And there are so many different kinds of series in the world that it might not be always obvious to you what test is appropriate. In some cases, more than one test will work, and that's fine. I'm not going to even go through the math of it. I'm just going to look at what test or tests I could use. So right now you're looking at question 1, I hope. Oh, darn it. I've got the solutions here, which aren't really helpful, I think. Good, they're gone away now. Right. I don't know if you caught the answer there, but what test do you think you should use for a series that looks like this?
Comparison.
Add one more word and you're good to go.
P-series?
That's not the word I was wanting. Limit comparison test. And you're right, it is a limit comparison test to a P-series. And the P-series, or I would compare it to a 1 over n. And so it's a limit comparison test. Only use a comparison test if it's something weird in the top, you know, like sine n or e to the 1 over n or something weird. Then use the comparison. Typically use limit comparison tests in these questions. All right, this one here I think is obvious. That's a scary thing to say, but I think it's obvious. There's something about that series that kind of makes it more likely to be one thing than any of the other tests.
Alternating series test?
Correct. What is it that screams out, use me, please? What's the thing in there that you can see?
-1 to the n.
Right, that's a very good clue. We haven't came to one, but I'm sure there's one in here. Suppose you get an n factorial somewhere. What's that going to scream out? What test?
Ratio test.
Right. So there are certain things that you see them, you know, yeah, ratio test. In this case, I think you could be able to say, yeah, I know an alternating series test. What about this one?
P-series?
Because of the n squared in the bottom, that kind of makes sense. The e to the n on the top's a problem.
Yeah, I take that back.
Yeah. This one is very strange because it's actually a test we hardly ever used. It's a divergence test. And the reason it's a divergence test is, won't that e to the n kill that n squared? Won't this end up being a limit of infinity? So it's a divergence test. Wow. What's that one? We haven't mentioned this test yet. So this is a new test, one that I haven't said yet.
Integral test?
I agree, it's an integral test. And it'll be a U-sub when you do it. This one isn't really one test. Isn't this piece here a P-series? And isn't this piece here a geometric series? So it's a bit of, you really have to do, what you really have to do is split it into 2 series and do those on it. Right, we've already talked about this one, but it has appeared, so go for it. What would you do with this one? What test? I think your mouth was
Ratio
moving, but I couldn't
test.
hear what you said. Agreed, ratio test. And the feature that makes that a ratio test is the bottom. Now, if you want extra practice at doing any of the tests, you can see this section you could use, and you can't damage your grade because you get 0 out of 0 no matter what you do. So it doesn't make your total homework grade at all. Right, this one is a, well, I do know what the answer is, but I don't think this one's that obvious. Douglas, what were you saying? Can't hear you yet.
Was it the root
Hit
test?
spacebar maybe? Yes, the nth root test, or the root test as the book calls it. What about that was the key to making you go there?
Everything is
What
raised
piece
to
of
the
that
power of
was-
k.
Or something like a K,
Yeah.
right? Agreed. Don't overthink 8. What test would work with 8?
Can you do a limit comparison test?
Oh, because of the 7 over n thing?
Yeah,
That would make sense, but
because
go simpler than that. A different test. I take it back. I was going to say you do divergence test, but that would only be true if it was n over 7. It's 7 over n, which is 0, and the tan of 0 is 0. I think I would have to do the integral test in that. Don't quote me in that one. I'd have to check, but that's what my gut is.
I think the
On the other hand, I think question.
the comparison test works for that.
It could do. As I said earlier, do you know that you can have more than one test that'll work? So you might want to check. Try it. I mean, if you've got time, try it out. This one I'm not going to argue about because I know what this one is. Because there's one feature in this that guarantees you have to use this test. What test is it?
Ratio test.
Yeah. I don't care where it is. If you see an n factorial, right, you're going to have to do a ratio test because none of the other tests can handle an n factorial, right? You can't differentiate it, so that means you can't use the integral test. There's really nothing obvious that you can use comparisons to it. 10 is a limit comparison test, and choose 11 sevenths, right? 11 over 7 to the k. Not we do that 11 over 4 to the k. Take the smaller one. Do a ratio test on that. How about this one? I think this is obvious. I hope it is.
And through.
What test for 12? Yeah. Isn't the key here that funny little guy up there? Yeah. Anything to the power, a whole big chunk of stuff to the power of n, or to the power of 2n, or the power of n squared is very often going to be the nth root test. Oh, we're almost finished. Last one.
Alternating series.
Yeah, it's back to that. Oops, the minus 1 to the n, alternating series. Right, so that section was basically just a whole mixture of possible series, right? Lots of different kinds of series. And the first job was to decide the test. Now and again, 2 tests, because both work. And then once you've decided what the test is, you would then go and do, you know, the integral test or whatever test it was, and you'd come up with the answer, convergent or divergent. I think if they were being fair, wouldn't they have a third one for inconclusive? Because when you do the ratio test and the nth root test in particular, can't you get inconclusive as an answer? Now, the reason they may not have the inconclusive circle is the ones that did use the ratio test probably worked, right? You'd get one or other as a response. But I think to be precise, they should have gave you 3 choices for all of them, just in case you got an inconclusive. Are we okay with us just looking at that as a set of strategies, but not necessarily doing them? Because the tests that you're going to do are tests that you've done questions on, right? So it's not new work. And the only new piece of this was being able to recognize what the test was. And that was the I think the job of that section. So if you can hold with me just for a little while longer, I will get us ready for our next section. Ah, darn it. Things went wonky on me. There we go. And shrink this back. That's good. It's funny, why can't I see it? I'm doing that habit of talking to myself, but it's the only way I can get intelligent conversations. Ah, here we go, found it. And our next section is 11.8. And 11.8 is called power series. And I close this off and go back in. I'll give you the intro to it. A definition. A power series is an infinite polynomial which is often written using sigma notation. So a power series is an infinite polynomial. Let's give you an example. Let's suppose I had a function and it was called a0 plus a1x plus a2x squared plus 3x cubed for eternity. And I want you to think of a0 and a1 and a2 and a3 as being constants. Then this is what we call a power series. In sigma notation, you would write it like that. And I just put in a 0 there where I should have put in, and then there we go. So just for neatness, I'll write it again. So an infinite polynomial, pretty interesting function, has an infinite number of terms. You might think that such functions were pretty stupid because they'll all end up being infinite. In other words, if you evaluated them at x equals 4 and x equals 1.7, the answer to these polynomials might be infinitely large, in which case they are totally useless. But in fact, we have found that many power series exist. In other words, you can find values for them at specific values of x. it typically does so for only a small range of values of x. Such as values of x whose absolute value is less than some number r. An example of that might be it only converges for values of x less than 1. If you wanted to see what that might look like in interval notation, it would be that. Oops. Or that. So power series, if they do converge, and converge just means if you plug a value of x in here, you get an answer that's a number, right? Converges to a number, you can get a value for it. Typically only do it for small ranges of x, something like this. And there's an example of it, and there's other ways of writing that same thing. So if I pick x equals a half, and I plugged it in here, it might converge to 22. If I plug in 7, it might converge, to another number. But if I plug in 50, the answer's infinite, right? It shoots off to infinity. So power series functions can converge. All power series converge when x is equal to 0. Dead easy to prove. Right, that's every power series in the universe, right? They all look like that. If I make x 0, don't all these terms become nothing? So, yes, they converge. And what do I know? I know the value is whatever A0 is. Not a very interesting function, but it exists at one point in space. I'm not writing this down, but a few power series, really, really rare, really exceptional. There are a few power series that converge for every single value of x. So you can pick any number from negative infinity up to plus infinity. And all of them converge. A very unique property that it will converge no matter what value of x you use. You hold on to that guy because he is rare. And it's probably something that is very useful. Most of them work for small ranges of value, which is typically -1 to 1 is one of the most common ranges that they work. So far, so good. Now, I need a colored pen. This number R, this R guy, excuse me, has a name. It's called the radius of convergence. So if you have a power series and it converges as long as the absolute value of x is less than 2, we would say the radius of convergence is 2. And this fella here, actually this fella here, this has a name as well. And this is called the interval of convergence. So every power series in the universe looks like this. In sigma notation, it looks like that. And very often, they put an I, say the interval is this. So what are we going to be asked to do in 11.8? Well, we're going to be given a power series, typically that looks like this. And we are going to find the radius of convergence and the interval of convergence. That's typically what we're asked to do. So here is our first power series. It's very like question 1. Excuse me. Now, do you know that this power series started at 1 instead of 0? Sometimes they start at 3 or 4 as well, but most of them will start at 0. It makes no difference. It just means the first term was nothing, so they didn't use it. That's pretty much all it meant. So how do we find the radius? And from there, we can then get the interval convergence. Well, we have to find out for what values of x does this fella converge. And we typically use the ratio test. Typically. There are some exceptions. The exceptions will be that now and again you'll use the nth root test. But most of the time it will be the ratio test. So in this question, because I'm taking this really slowly because it's sort of like our template, would you agree that's what AN represents? The entire package including the -1 to n, right? And AN plus 1 would be that. I wouldn't normally write that down, but as I said, this is a kind of template for the process, so I want to write as much as I think is necessary. Now, the ratio test then says the limit as n tends to infinity of the absolute value of AN plus 1 over AN. Now, here's a little minor change. When we did the ratio test, typically, didn't these absolute values disappear really quickly? You know, because the answer's positive, we didn't need it. In these questions, don't lose the absolute value. Keep them all the time. It's important that you don't lose them. So this absolute value is going to be everywhere. So it's going to be now the limit as n tends to infinity. Now, if you take this guy on the top and that guy on the bottom, you get 4 -1 to the n plus 1, n plus 1, x to the n plus 1. And on the bottom, you get this fella. Are we comfortable with what I did there? AN plus 1 on top, yeah. Right, just like normal ratio test, we are going to start killing things off as best we can. Would you agree that those 4s kill each other off? Right, they cancel out. Technically speaking, whoops, there's an n there. Don't the -1 to n's and -1 to the n plus 1s and any other -1, don't they just get killed off by the absolute value? So I'm just killing them off, getting rid of this. I can take this guy and cancel with that guy, but when I do that, there's an x left on the top. So that's kind of what it looks like after the cancelling. Quite a lot simpler than it did. So far, so good. Now, the next step is I'm going to split this fella up. That guy and the x guy. What will the limit of n plus 1 over n be as n tends to infinity? You should be able to do that in your head. What would n plus 1 over n get you as n goes infinite?
1.
1. And so 1 times the absolute value of x gets you the absolute value of x. And technically speaking, I didn't really need that guy, did I? Because I already took care of it. And x doesn't have any ends in it, right? So it's a fixed value. So in this case, the ratio test says the ratio of this happens to be that guy. That's the limit. Normally that would be 42 or a half or 7 or 3/4, right? It'd be things like that. But it's this guy. What does this have to be less than for convergence? In the ratio test, what does the limit have to be less than for the series to converge?
1.
I have now found the radius of convergence. Remember, the radius of convergence is this number here, right? The absolute value of x is less than a number. Can you see the absolute value of x is less than 1? The radius of convergence is r equals 1. So in your homework, you have a box that looks like this, and you put 1 in it, and that would be the answer to part A. So as long as the absolute value of x is less than 1, this power series, but it's called a power series in these stories, this power series will converge. Now, what does that look like as an interval? Because that's kind of the second thing they asked, right? Find interval of convergence. Well, if the absolute value is less than 1, isn't that the same thing as that? Okay, and in interval notation, that's that. And now I'm going to annoy you by writing this down. And you say, what on earth is the word possible doing there? The reason why this is the possible interval of convergence is because the ratio test will definitely converge if x is less than 1. So those are definitely values that you can use, anything between -1 and 1. However, you must also test the two endpoints. And the two endpoints are x is -1 and x equals 1. So we have to test this series with these two numbers. Now, there are lots of things that could happen. Do you know if x equals -1, I plug it in here and it converges? That's great. X equals 1, I plug it in and it converges. So I could get everybody including -1 and 1, right? That could be my interval of convergence now, right? Because the two endpoints work. I could get that side doesn't work and this side does. I could get this side works and that side doesn't. Or I could get none of the endpoints work. But your interval of convergence will always be one of these four things. And we now need to find which it is. So now I'm going to go back to my series, my power series. And we are going to pick one of the two endpoints. Which one do you want me to test first? Do you want me to try the -1 or the 1 first? Because I'm going to do both, but which one would you like first?
-1.
Okay. Now that means that you replace the x with -1. Let's see what that looks like. Well, if I do a little bit of joining together, isn't -1 to the n times -1 to the n the same thing as -1 to the power of 2n? Can you imagine multiplying them together? Something to the n times something to n, something to 2n. Oh, that's good. What is -1 to the power of 2n? What's that equal to?
+1.
Every single time. Now, don't overthink this one. Does that diverge or converge?
Diverge.
I mean, it's a kind of screaming, technically the divergence test, but it diverges. So we'll try x equals 1 then, the other endpoint. And in this case, n equals 1 to infinity, 4, -1 to the n, 1 to the n. Well, 1 to the power of n is still 1, so what you're looking at is this guy. And again, don't overthink it. A lot of the time, the two endpoints are very simple series that you should be able to look at reasonably quickly. Do you think that converges or diverges?
Diverges?
It does. Technically, I could do the alternating series test and prove that it's increasing. That'll kill it. I could do basically just common sense. Doesn't this go -4 add 8 plus 12 -16 add 30? I mean, it just keeps on getting bigger and positive, then even bigger and negative. Can you imagine an oscillating getting worse each time? It's a diverge. So since both of those are not any use to me, I now can take out the word possible interval convergence and now replace it by, this is the interval of convergence. So that means we can have a function, f of x, equal to n equals 1 to infinity, 4, -1 to the n, x to the n, and as long as you keep x in the range -1 to 1, this will exist as a function. Just the same way that sine x and e to the x and log x and all the, x cubed plus 1 exists as a function. This just has the property that it only exists from -1 to 1, right? Whatever it looks like, and I have no idea what it looks like, but that's what it might look like, right? In that range of values. So you might think, I wonder why, I mean, it's kind of interesting, but I wonder why we even worry about these power series. What is their use? Well, here's a remarkable thing. Do you know that every function in the world that you know about is a power series to some extent? Well, x cubed is a power series. Isn't it just a power series where most of the numbers are 0, meaning most of the coefficients are 0? But technically, it's a power series. Do you know e to the x? You'll find out later in this class. E to the x is a power series, or can be written and represented as a power series, is a better way to say it. So can sine x and cosine x and hyperbolic tan and you name it. Square root of x can be written down as a power series. Every single function in the world can be written as a power series. And if it can be written as a power series, we can then use it to analyze it in a different way than we usually would do. Very powerful technique. Power series, cool stuff. That question was a really long one, but it gave us the kind of template, right, for how we're going to do it. So the next one I pick is going to be a little bit quicker, I hope, and maybe a little bit smoother. So just going to scroll down, pick this one, question 3. Find the radius and interval of convergence of this guy. Here we go. The limit as n tends to infinity, an plus 1 over an. Okay, n plus 1, n plus 1, n plus 1 to the 7. Turn me upside down, n to the 7, negative 1 to the n, x to the n. Limit as n tends to infinity then. See who we got. All those get killed. That guy will kill that guy and leave an x on the top. I have an n to the 7 and an n plus 1 to the 7 left over. I'm going to call this the limit as n tends to infinity of that guy, absolute value of x. Okay, now I'm going to do a quick cheat in that, but I think I can get away with it. What do you think the limit of this is going to be as n goes infinite? I mean, I could do L'Hopital rule 7 times and prove it to you. I could FOIL that out and divide top and bottom by n to the 7 and prove it to you. But just looking at it, can you make a reasonable guess at what that limit is?
1.
Yeah. So, quite boringly, we get that guy again, which means it converges if it's less than 1. So I now have my radius of convergence. My possible interval of convergence, I would then test -1 and +1. Let's see what they look like. I'll do -1 first. The endpoint -1, what does that get me? Sigma n equals 1 to infinity, -1 to the n, -1 to the n over n to the 7. That becomes n equals 1 to infinity over n to the 7. Okay, I'm going to skip a line here. If you put those two guys together, don't you get -1 to the power of 2n, but isn't that just 1? Okay, look at that guy. Converges or diverges?
Converges.
Okay. If you wanted to prove it, wouldn't it be, it's a P series where P is 7, so it converges? Okay, let's test the other endpoint, x equals 1. Well, we get -1 to the n, 1 to the n, which doesn't really get you anything except 1. You get that guy. Again, most of these endpoint tests are things you can very often just do in your head. Converges or diverges? Correct. If I wanted to prove it, wouldn't it be an alternating series, and eventually I'd get the answer? But I think, hopefully, by now that you've seen enough to just know that that's going to work. So that makes the interval of convergence not all the numbers between -1 and 1, but all the numbers including -1 and 1 and between. when you do these questions, I don't expect you to spend a lot of time on figuring out whether these converge. If you're not sure if it converges, then do the test the formal way and find out. But for many of them, I hope you can just eyeball and say, yep, that one's definitely going to make it, or no chance. I mean, that's your two choices, right? It makes it, it converges, or it's no chance, it diverges.
Professor,
Are we good? Yes.
I'm just confused of how we got x by itself over when we were doing the
Oh, right, let me go back to here. Right, what we had on the top was an x to the n plus 1, and over here we had an x to the n. So if you imagine them being above each other, can't you cancel that with that and leave one x behind on the top? Think of it like x to the n plus 1 is the same thing as x to the n times another x. And x to the n on the bottom. Can you see you're left with an x? I can imagine this happening. Can you imagine a different question where you had an x to the n plus 2 on the top and an x to the n on the bottom? And they would cancel. How many x's would be left now? Would it be x or x squared?
it would just be x, right?
We have a 2.
Oh no, because we cancel
don't
out
have
the
it.
n. So x
Right.
squared.
Another way, just different ways of looking at this situation. If you think of x to the n plus 1 again over x to the n, if I say to x to the 7 over x to the 6, don't you take the top guy and subtract the bottom and whatever's left is the answer? Well, if you think of that rule, it's just another way of looking at it. Top guy, take away bottom guy. Can you see you're left with 1? So you got to figure out what way of looking at it makes more sense to you, because then you'll do it right the next time it happens. Right? So I know, did that way make more sense than this way or whatever? It's really different people see things differently. We good? Let's try. Okay, one really quick one. Which one should I try? Oh, God, yes. This one is my favorite. X to the n over n factorial. Now, it is the ratio test, but that's no biggie. They're all ratio tests, virtually, at least the ones we've seen so far. You have x to the n plus 1 over n plus 1 factorial, and then you switch the guy around, you get that. So far, so good. Okay, let's do some cancelling here. We've done factorials being cancelled before. This is n factorial. This is n plus 1 factorial. When you cancel those two guys out, what's going to be left on the bottom?
N plus 1.
Yeah, great. Are we kind of comfortable with that because we've seen it a lot, right? And won't these two cancel out with an x? I tend to separate the x's out and keep whatever n's are left over. Right, time to make this go infinite. Would you agree you could just do a brute force on this? Couldn't you just replace the n with infinity? What will 1 over n plus 1 be then if you make n infinite?
0.
And won't 0 times this, because this is a fixed number, be 0? So I just wanted to show you an example of a question where you didn't just end up with the absolute value of x, because that's not the only answer you can get. Can you see here we got 0? This is quite interesting to interpret because it's different from the others in the sense that isn't that guaranteed to be less than 1. So doesn't that mean it will converge for every single value of x? It doesn't matter what x is, it's going to converge. So I guess you could write it like that. Isn't the radius convergence infinite? So that's how you would describe this situation, where if every single value of x works, wouldn't the absolute value of x be less than infinity? Be a very weird way of saying it, but that's what it's saying. And won't the interval of convergence be every single number in the universe? That power series will converge for any value of x you like. 42, 42 billion, minus 30, whatever. That's a power series. That is a rare event in power series, that you can have a power series that converges no matter what you pick for x. That means its radius is infinite and its interval is minus infinity to plus infinity, right? That's where the x's are. I'll show you this on Monday. But that power series is actually e to the x. Equivalent to. You wouldn't have thought e to the x was an infinite polynomial, would you? It doesn't strike you as even being very polynomial. Shouldn't polynomials kind of wobble? Because that's what they all do. Right? They, you know, like a wavy line. But e to the x is actually represented by that. So will you all say hi for attendance? And anybody who has any issues, questions, hang about at the end and we'll do them for you. But that is phenomenal. Okay, guys, bye-bye. If you say a tie, any questions, of course, we'll hang around.
Thank you.
You're welcome. See you Monday. Okay, who wants to start first? Who's got a question?
I just had a quick question of where to find my grade for the test.
It was sent to you as an email. And I used the email that I have on file. So I would probably look at your Canvas email, which is, I think, where I got most of them. But I also used the WebAssign email sometimes because I couldn't get a Canvas one that would work. Not everybody got theirs because the email that you've got on file doesn't work, or you don't look at it. I don't know what. If you haven't got it, shoot me an email and I will copy that email into my spreadsheet. So I'll use that one next time and I'll send you back your grade on that same email. So if you can't find it, that's where it'll be.
Okay,
right.
Thank you.
Why is it there?
Yeah,
I was assuming you were looking for it. Okay.
Yeah, it's in my.
Right, if you go through. Okay, so when you go back there and you look at it, if there's some questions, I don't know why I get question 4 wrong, you can do that. If you want to hang about and just listen to any other questions, feel free to do as well. Okay, Sammy, you got a question?
Yeah, so
Or a topic? Yeah.
I don't know why I don't remember it, but I was hoping that you could explain what the comparison test is compared to the limit.
Compared to the limit comparison test, or you want both?
I know
Which
the
do
limit
you want?
comparison test, just the comparison.
Oh, the comparison test, okay. So the comparison test should typically only be used when you have a fraction, most commonly anyway, a fraction where the numerator is weird. That's most likely. So I'll give you an example of what I'm talking about. Something like that, right? So, call that question 1, call that question 2. In question 1, the original function is this fella. I'm going to compare him, right, to 1 over n squared, which is typically what you do with a limit comparison test. Right? Now, the difference here is, do you know that 1 over n squared converges? Can you tell just by looking at a p-series, it's 2, it converges, right? And so this fella should converge. If you're not sure, why is that a 1? Well, e to the 1 over n is pretty messy, but can you imagine as n gets bigger, doesn't it just become e to the 1 over 1/20th and e to the 1 over 50th? It becomes a number that is very similar to 1. So all I need to do in the comparison test is to take this guy and prove that he's less than or equal to some guy that looks like him. Now you say, well, why did I turn that into a 2? Because at some point, won't this be less than 2? At some value of n, won't this eventually become less than 2 for all its values? So what I'm saying in the comparison test is that this guy is always going to be less than or equal to this guy. And then what the comparison test says is, if you're less than a converger, you converge. And the argument for that is, if you stick a sigma in front of these, since this converges, doesn't this equal some number like 42? And isn't this less than 42? We don't know what it is, but we know it's less than or equal to 42. If you're less than or equal to 42, doesn't that mean you have to converge to a number because you can't be infinite? It's that kind of argument. Now, sometimes, if I was doing this one, for instance, would you agree that I could get away with that comparison? I don't know what sine n does. Doesn't it bounce about all over the place, and sine squared as well? But would you agree that it's 1 is as big as it gets?
Yeah.
So won't this be bigger than that? What do you know about this guy?
Converges. Or wait, no. Yeah,
So,
it converges.
This guy converges. Now I can go the other way. Take that guy. Now, he behaves like him. Would you agree that that's true?
Yeah.
Right? That diverges. Isn't he bigger than something that diverges? So the comparison test says you diverge. But the comparison test should only be used in situations where typically the top is something weird. Weird could be anything. Inverse tan of n over n cubed. Cosine a over n squared. E to the 1 over n squared. N to the 4. You know. Something weird on the top. If you get n squared plus 1 over n to the 4 plus 1, won't you use the limit comparison test now?
Yeah.
And you use the limit comparison test because you can't really set up you are bigger than me or you're less than me when the top and the bottom are messy like this.